This module is the first of 3 modules where we will be walking through the main theoretical ideas behind mean variance portfolio selection. We'll first define what a portfolio is. We'll talk about what the return and risk of a portfolio is going to be. We're going to define what an efficient frontier is. We're going to define how an efficient frontier changes when there's a risk-free asset and how all of that leads up to the capital asset pricing model. The overview of what we're going to be talking about here is that we're going to define assets, we're going to define portfolios, we're going to define how to measure random returns on assets and portfolios. And for the mean variance optimization, as the name suggests, we're going to quantify the random asset and portfolio returns by their mean and variance. We're going to define something called mean variance optimal portfolios or mean variance efficient portfolios. We're going to define something called the efficient frontier and the portfolios that lie on this efficient frontier, and how does one compute them. Along the way, we are also going to talk about Sharpe ratio and Sharpe optimal portfolios. We're going to define something called a market portfolio, and after defining the market portfolio, we'll get to something called the capital asset pricing model. These are the various modules that we're going to be walking through in this bigger topic of mean variance optimization. So what's the goal here? What I really want to do is I've got a certain amount of money and I want to split it among various assets that are available for investment. I'm going to characterize an asset by its price. More often than not, I'll be interested in returns on these assets. I'm going to invest in them today, I'm going to sell them tomorrow, and whatever difference is the return that I make on it. And I would like to maximize this return in some appropriate sense. So I'm going to define the random gross return on a particular asset to be simply the price one time step later. A time step could be a quarter, could be a year, could be 6 months. So it's PT plus 1 divided by PT. The net return is simply RT minus 1. It's going to be PT plus 1 minus PT divided by PT. I want to point out that both RT and little rt are random quantities. These are random because the price at time t plus 1 is random. Price at time t, which is right now, is known, but the price at time t plus 1 is random, and therefore these returns are going to be random. I've got d different assets, and I want to split an amount capital W that I'm going to assume is strictly positive. This is the capital that I have, and I want to split it over the d assets that I have. W sub I will be the total dollar amount that I've invested in asset I. If Wi is greater than 0, I'm going to say that that's a long investment. If Wi is less than 0, it's going to be a short investment. For the purposes of modeling, we allow W to be both positive or negative. R sub W will be the net rate of return or net return on the position W. By position, I mean the wealths in the various assets. So what is the definition? It's simply the total value of this one time step later, which is the gross returns on each of the assets times the amount of money that was put into those assets, minus the initial wealth, which is sum of the W's, divided by the initial wealth, which is capital W. If you do the math, this 1 can be subtracted from Ri, and you end up getting this is going to be the net return little RIT Wi divided by the sum of the Wi's. You rearrange them a little bit, and you end up getting that the net return on position W is the net return on each of the assets RIT, which is a random quantity, times Wi divided by capital W. So what is important to the net return is not the absolute amount of wealth that is invested, but the relative amount or the fraction of the total wealth that is invested in a particular asset. So instead of worrying about positions, we just have to consider a portfolio vector. So X is a portfolio vector. It could be positive or negative. Xi's represent the fraction invested in a particular asset. So sum of the Xi's must be equal to 1. One thing that I want to point out here is I've been talking about time t. In reality, the return that you get, whether it's the gross return or the net return, changes over time. The random properties change over time. The actual values that are realized change over time. But in this set of modules, we are going to be looking at a very myopic investment strategy. I'm sitting at a particular time t. I only want to invest at time t plus 1. When we get into more advanced topic, we're going to talk about how to extend this idea to a multi-period optimization. People are interested in multi-period optimization because at the end of the day, they want to save money for retirement, want to save money for buying a house, and so on, which is not a one-period problem, but a multi-period problem. A multi-period problem is not simply a concatenation of one-period problems, because the space over which you can optimize becomes much larger when you look at multi-period problems. But in this set of modules, we're going to be concerned only with one-period optimization, 1 quarter, 1 year, and so on. So how does one deal with randomness? The return on the portfolio, R sub x, is going to be defined as Ri xi. And notice over here I've dropped the Ri, the time in the Ri, because I'm focusing mainly on myopic optimization. This is a random return. Why is it random? Because each of the net returns Ri's are going to be random. How does one quantify these returns? Should I simply look at maximize the expected value? Is that the right thing to do? Should one be worried about the spread around the mean? So the expected value or the mean value tells you what happens when you repeatedly invest. Most of us don't have the ability to repeatedly invest. If we go bankrupt, our investment is over. You don't have the ability to return from bankruptcy, then you might have to worry about what happens to the spread around the mean. How does one quantify the spread around the mean is going to be a question that we'll have to deal with. The way we're going to do this in these set of modules is we're going to talk about the mean, and we're going to quantify the spread around the mean by the variance. So the values defining the asset returns are going to be the mean return, which is the expected value of the net return, the variance of the asset return, which is simply the variance of the random variables. Notice the mu i's and the sigma i's are assumed to be independent of time. Again, either the market itself is stationary, or we are only interested in myopic investment, therefore we don't have to worry about time. The covariance between the asset return is the covariance between a random return on a particular asset I and an asset J. Correlation, again, it's between two assets, and there's a relationship between covariance and correlation. Covariance is nothing but the correlation times the volatility of asset I and the volatility of asset J. All parameters are assumed to be constant over time. Now, I'm going to characterize the random return that I get on a portfolio by looking at the expected return of the portfolio and the variance of the return on the portfolio. So the expected return on a portfolio X, mu sub X, is going to be the expected return on the net return of that portfolio, R sub X. By using linearity of expectations, we end up getting that this is nothing but the expected return on each of the assets times the fraction invested in that asset, Xi. So it's just mu I times xi summed from I going from 1 through d. The variance of the return, again, just by the expression, it's the sum of Ri times xi, the variance of this random variable. And if you expand it out, it becomes the covariance of Ri and Rj times xi xj. Here's just a simple example to try to work you through it. So I have two assets with normally distributed returns with mean mu and variance sigma squared. So R1 is one asset. It has a mean 1. And it has a variance 0.1. R2 is another asset. It has a mean 2 and has a variance 0.5. The correlation between these two assets is negative 0.25. So if you translate this statement into those parameters, mu 1 is 1, mu 2 is 2, sigma 1 squared is 0.1, sigma 2 squared is 0.5, sigma 1, 2, which is the covariance between R1 and R2, is going to be the correlation, whose number is right here, times sigma 1, sigma 2. You plug in the answers, you'll end up getting it's 0.0559. In the two-asset market, portfolios are very easy to define. Remember, portfolios were the fractions invested. So if I invest fraction x in asset 1, and since the fraction invested in asset 1 and the fraction invested in asset 2 must add up to 1, I should invest 1 minus x in asset 2. Later on, we will see how we can use this x1 minus x to try to do efficient portfolio selection between these two assets. Plugging it into the formula, the expected return on this portfolio is going to be sum of mu I xi 1 through d. Two assets, the first asset has x, its expected return is 1, so it's 1 times x. The second asset has 1 minus x, its expected return is 2, so the total expected return that you get on this portfolio is x plus 2 times 1 minus x. What is the variance associated with the return of this portfolio? The formula is sigma ij xij xij summed from I equals 1 through d, which can be equivalently written as sum of I going from 1 through d sigma I squared xi squared plus 2 times j greater than I sigma ij xi xj. Plugging it in, 0.1, which is the variance of the first asset, times the investment in the first asset squared, 0.5, which is the variance of the second asset, times the investment in the second asset squared, 2 times the covariance between the two assets, which was just computed here, times the investment in the first asset and investment in the second asset. This exact thing can be generalized to multiple assets, and that is what we'll do in later modules. Okay. So first thing we want to talk about is that diversification, or thinking about the spread around the mean, is important because it reduces uncertainty. So let's consider a very contrived market. I have D different assets. All of them have the same expected return mu. All of them have the same volatility sigma. And the correlation between the assets is equal to 0. So each of the assets is basically identical. And now let's think about two different portfolios. In one portfolio, X, I invest everything in asset 1. In the other portfolio, I equally distribute my initial dollar over all the assets. So in every asset, I invest 1 over D. Both of these are portfolios. The expected return of the first portfolio, which is X, is simply the expected return of asset 1, which is mu. The expected return on the other portfolio, Y, which equally invests in all the assets, is going to be the average of the returns of all the assets. Since each of them has the same return mu, the average is also going to be mu. So if we were just looking at the expected value, the two of these two portfolios cannot be differentiated. They both give me the same expected value. We should be as happy investing in X as we should be investing in Y. But if we are, as we should be, interested in reducing uncertainty, then perhaps these two portfolios are different. So if you look at the variance of the returns of the two portfolios, what do you get? Sigma X squared, which is the variance of portfolio X. We know that that just invests in asset 1, so it's nothing but volatility squared, sigma squared. What happens to the variance of portfolio Y? If you plug in the formula, every one of them has 1 over D invested in it, so it's 1 over D squared, sigma squared. There are D terms, so ultimately you get that the variance associated with portfolio Y is sigma squared over D. Think about D of the order of 100. Say I'm interested in the S&P 500 index. So in the one case, I get volatility sigma squared. In the other case, my volatility has dropped down 100-fold. So just by diversifying between assets, identical assets, now I have been able to reduce my volatility a lot. The mean variance portfolio selection problem, in the end, generalizes this idea. Here I'm taking a very simple problem. All the assets have the same return. All the assets have the same variability. And I know that equal spreading is the best thing. Now what I want to do is move this idea to a case where the mean returns are not the same, variances are not the same, the covariance may not be equal to 0. How does one think about this problem? How does one compute efficient portfolios, meaning portfolios that have a good mean and variance properties, is going to be the main focus of these sets of modules. So in 1954, Markowitz proposed a portfolio selection strategy. In his model, he suggested that the return, and the return has been put in quotes, I want you to read this more as the benefit coming from a portfolio, to be the expected return of that portfolio, and the risk associated with the portfolio to be the volatility of that portfolio. And what he suggested was that these are the two quantities that are going to be interesting to investors. They would want to increase their return and decrease their risk. So what I'm plotting over here are the returns on some random portfolios. In the next module, I'm going to show you a spreadsheet which shows you how these random returns were generated. I had 8 different assets, the details of which will be in the spreadsheet. I randomly generated positions on these 8 assets, figured out what the return is going to be, figured out what the volatility is going to be, and I plotted a point. So all of these blue dots are actually the various portfolios randomly generated. And the efficient frontier, this line over here, is generated by the following procedure. You pick a particular value of volatility or risk and try to compute the largest return that you can get on a portfolio that has risk no larger than a particular bound. So let's say sigma bar is the bound here. Figure out a portfolio, compute a portfolio, and I'll show you in the spreadsheet how these portfolios are computed, which has the largest return with risk not exceeding sigma bar. And that point will be right here. And similarly, you take different values of these Sigmas compute out what is the maximum return that you're going to get, and this blue line is generated by computing the maximum return for a given value of risk. That frontier is called the efficient frontier. Why is it a frontier? Because all portfolios, all feasible portfolios must lie below. This is all the part that is feasible. For any portfolio that you choose, its risk and its return values must be below the line. All of this space is unachievable. You cannot create a portfolio whose return and risk point lies in that region. Why is that? Just the way it's computed. I take the value of sigma, which is the risk, I compute the maximum possible return that I can get, and that's how I get this point. This return up here is not achievable. So everything above the frontier is not achievable. Everything below the frontier, below or equal to the frontier, is achievable. But I would never want to be below the frontier. If I have a point over here, its risk is some quantity over here. Let's call it sigma 1. My frontier tells me that I can create another portfolio, a different portfolio from the one that generated that point, whose return is going to be right here. It's going to be on the frontier. So I would never want this portfolio. I only want portfolios that lie on the frontier. Above the frontier, unachievable. Below the frontier, inefficient. Right at the frontier is the place where I want to be. So the question that we will answer in the next few modules is, how does one characterize this efficient frontier? How does one compute efficient, or sometimes I'm going to call it optimal portfolios, portfolios that lie on this efficient frontier? There are three different ways in which you can compute the mean variance optimal frontier, that line that I showed you before, which tells you the maximum return for a particular value of risk. One way is to minimize risk for a target return. You can set the target return that you want. You want to make sure that the expected value on the portfolio has to be greater than equal to R. And among all portfolios that satisfy that, you want to minimize the variance or minimize the volatility, which is equivalent. If you expand this optimization problem, you can write it as sum of xi's is equal to 1. So this is a portfolio constraint. And here you're saying that the expected return on that portfolio must be greater than equal to R. And this expression here just expands out whatever is written over there. And for those of you who are mathematically sophisticated, this expression is nothing but the vector x transpose a matrix of covariance times x. And what is this matrix? It's sigma 1 squared, sigma 1 2, sigma 1 3, and so on, sigma 2 1, sigma 2 squared, and so on. So this is the variance covariance matrix. And this expression there is simply x transpose variance covariance matrix times x. An equivalent way to get the entire frontier is going to be to maximize return for a given value of risk. Maximize mu of x such that sigma squared of x is below some target number sigma bar squared. If you write this in terms of the xi's, it becomes sum of the xi's must be equal to 1. Again, the portfolio constraint. X transpose sigma x, or sigma ij xij summed, must be less than or equal to sigma bar, and you want to maximize the expected return. There is yet a third way of trying to get the entire frontier, and that is to maximize a risk-adjusted return. So maximize over portfolios x, mu of x, the expected return, minus tau, which is called a risk aversion parameter, sigma x squared. So the risk aversion parameter is always greater than 0. You don't like risks, therefore you want to subtract from the expected return a certain quantity that depends on the risk. If you again expand this expression, you get its sum of xi is equal from xi must be equal to 1, which is the portfolio constraint, and this is just mu of x, and that is sigma x squared, and that's the tau there. What do I mean by saying all these three will generate the same frontier? There are free parameters in all of this, all of these formulations, r, sigma bar squared, and tau, and as you crank up these parameters, for different values of these parameters, you will write out the same curve. And in the